later. So for more information, you can also check a free session. It's a great tool for deeper analysis of the Oracle kernel. Okay, this is a great tool that you can investigate, that can use, for example, for stealing the password of our colleagues, and maybe if you're using the same password as social media account, hack his social media account. That's great. Okay, have fun with it. Okay, so besides tracing core architecture, you can also trace peer sequels. Can be great also. You can, for example, have a script to trace target peer sequel program, display, for example, which subprogram is executing, which line number, so the peer sequel execution flow. You can also, for example, extract different peer sequel function arguments. For example, here we are displaying the DBMS output port line subprogram argument without even changing anything to the Oracle database. So just have to execute our script, and in this case, this is only read-only script, so it is safe to execute. Well, safe. It depends. And it can extract the information we want. Another use case will be this one that's similar to Stefan's session yesterday. So this script allows us to check hidden memory consumer inside the target peer sequel program. For example, it can give us actually which subprogram name and line number is responsible for this, the source of this high memory consumption inside the target peer sequel program. And there is many custom things that we can do using this different tool. And but besides the monitoring the kernel and the system, we can also use a different tool to do some kind of monkey patching. So, for example, we can say we can modify a different function argument or function return value, or maybe execute custom C code. This can be great. For example, based on that, you can write a mini database firewall. In this case, the script displays every statement issued from specific IP address in specific target database, and it will block every blacklisted statement. So basically, if you have a client issuing a blacklisted statement, in this case drop table test, what we're gonna do is just replace the SQL statements with the end of line statement, so that the client will receive not the invalid SQL statement. We could also replace this SQL statement with any statement you want. It can be some kind of SQL translation framework, or maybe maskless data, or basically you can do a lot of things. Another use case was also to write some software cracks. It can be useful to bypass some unwanted restriction in the Oracle software, or any software, by the way. So, for example, here I'm trying to install the Oracle database in a target platform that was not supported, and I'm receiving I cannot continue because I'm missing capabilities, okay? And then but I want to continue, I want to test this database, I want to have fun, and then it give me no. So I must bypass this. So what we're gonna do is you should check in which exactly in which function this bloody message is. So sorry. in which function this check is implemented. So. To do that, also we're going to use the Intel-Pin tool first to analyze the Oracle executable and check in which function this restriction is implemented. And then using dynamic tracing, we're going to tweak this function. For example, this function was returned 0, maybe it means false. You are missing this, so I'm going to modify the return function so that return 1 for true, I got this, okay. And then I can continue execution. And this is only use case, and basically you can do many other things, many other crazy stuff that you want. Oh, I think I'm going to go quickly. Huh? I don't know. Okay, sorry. I'm going to slow down.
You can repeat.
Okay, just switch to another part of the session. This part is too long. Deeper, in this part, we're going to try to check how we can get a deeper look at CPU utilization. So in this part, we're going to try to answer questions of, for example, which program hotcode path is responsible for high CPU utilization, how efficient this program is using our processor, and what is our processor bottleneck. So let's begin with CPU profiling. So most of the Linux advanced tracers are capable of lightweight profiling of CPU utilization by stack sampling. And then we can grab this profiled data of stack sampler and visualize it using a flame graph. So basically this gives us a full picture of the system and allow us to quickly and efficiently to find our hotspot path. We can also customize this flame graph with application context. For example, it can be useful to analyze high CPU utilization inside an overweight event. Is waiting what is burning CPU, or maybe to analyze high CPU utilization inside the target page SQL program with actual line number, as it top page SQL subprogram name and Oracle core function. I mean, may add a lot of things. So, but we may ask at this point, but we may ask at this point, what those functions are doing when they were on our processor? Are they running or stored? So there is a brief blog post from Brenda and Greg stating that basically we may think about our CPU utilization is wrong. We maybe think our processor is busy making forward progress with instruction execution. But in reality, in most common cases, we may store waiting for some resource, for example, for some memory and float output. So how to know exactly what's going on inside our processor? So to answer this question, we need to take a look at another type of event known also as hardware event or also performance monitor counter event. So this is basically an instrumentation of low-level CPU activity. It allows us, for example, to count how many cache miss, level 1 cache miss, level 2 cache miss, or instruction retired in our processor. There is hundreds of hardware events available in new microprocessor. They are very well documented in Intel reference guide. We can also use the perf list command to list the different hardware events available on our platform. So this different hardware event can be combined to construct high-level metric, such as the instruction per cycle. So by the way, instruction per cycle is a good starting point for analyzing CPU efficiency or how efficiently our program is using our processor. For example, basically, the more instruction you execute per cycle, the better. It's a simplification. And here you can use the perf tool to analyze the IPC for a target process. You can also analyze CPU efficiency at the function level. Here, for example, using a CPU flame graph, you can spot here that the Oracle kernel function get consistent rate is one of the slowest functions in our program, because it was running with the highest CPI or lowest IPC in this case. So basically, based on the value of IPC, you can also begin to do some assumption about potential performance problem that we may be hitting on our processor, and also begin to decide about different tuning strategy. For example, we may say if the value of IPC is lower than the specific value that we can calculate using different dummy workload, then you are likely memory bound. And if the value of IPC is bigger than the specified value, then we are likely instruction bound. And depending on the case, we may decide to use different tuning strategy. But the thing here is that we are guessing, and the value of IPC alone cannot be used to find exactly where we are wasting our precious CPU cycle. There is a lot of type of problem that we can hit on our processor, and not all of them are bound or related to our memory subsystem. So, how to know exactly what's going on inside processor, what type of problem we are hitting, because different problem type can have different tuning recommendation. So, to answer this question, you can use the different available hardware event to dig deeper. But which metric or which hardware event is relevant in our case? Maybe you're gonna begin with checking the branch miss prediction H ratio, branch miss prediction statistics, or maybe you're gonna check the transaction look side buffer statistic, or maybe the level 1 or level 2 cache statistic. So you are not going to check all this metric randomly until finding what type of problem we are hitting in our processor. What we need at this moment is methods. We need a systematic way to dig deeper in our processor performance. And then we're gonna check this middle. So today we're